Good afternoon, everybody. I am Rachit Manchanda, and today I'm going to discuss with you embedded system scenarios, and most importantly, the role of embedded system in wireless sensor network. And I'm also going to discuss with you what are the latest trends in wireless sensor networks and what are the challenges in embedded system. And I'm going to relate those challenges in wireless sensor network and how we can avoid them in order to make our design. So these are the outlines. Very first, I'm going to discuss introduction to the embedded system. Secondly, we go through with the what is wireless sensor network, its architecture point of view, and where actually we require the embedded system there. And of course, we have to discuss the digital signal processing part. This is the main key of this lecture. What kind of difficulties we are going to go through with while we are having the digital signal processors. And next, the compressive sensing. This is the most emerging field today, compressive sensing. That compressive sensing, that how we can avoid the problems that we are having in digital signal processors. So that can be avoided by using the concepts of compressive sensing. And next, the concepts of compressive sensing are used in today compressive data gathering, which is also used in wireless sensor networks. And the last is power aware architecture, which is very important from embedded system point of view, because this is the one of the challenging point of view for the designers, that how they can make a power aware architecture. So let's start with the introduction to embedded system. You're already aware with what is embedded system is, so I'm just going to go through with it. What is embedded system? The simple and the more precise definition of embedded system is that means any computing system which is not a general purpose computer. Means I'm talking about the computing system rather than any other general purpose computer, obviously, which are not having the keyboards or the monitors. They come under the category of embedded system. Means we are going to put a small computer in an appliance, and then it performs the computing tasks. Obviously, it is having some software part that is embedded into the hardware, some pre-programmed instructions which are going to perform some application specific task, or they might be the part of some larger system. That is the meaning of second line, that is hardware and software. And obviously, when we are talking about the embedded system, the system means here the things are going to be performed in an organized manner, in a planned manner. So that's the part of the software where the programming part is coming into the picture. And the most important thing is that the embedded system processed the instructions in order to control the electromechanical equipment. This is the most important word. When I say electromechanical, that means I'm talking about both the electrical and the mechanical processes on a single chip. And strictly speaking, I can say that manual operating switch can act as an electromechanical equipment, but we usually took this definition in a respect that we are using the electrical signals to generate the mechanical movements, or we are using the mechanical system to generate the electrical signals. Why I'm discussing this word so importantly, electromechanical? Because this is the key topic of my wireless sensor networks, because with the help of these electromechanical systems, plus with the concepts of digital electronics, that led to the development of microsensors. So that's why I'm emphasizing on this particular keyword, that is electromechanical systems. So this is a small block diagram of embedded system. The sensors, obviously, I have to take data from the outside world if I'm talking about any real-time application. So I need a sensors. There could be a various type of sensors. It depends what kind of physical variation you are measuring. It might be a thermocouple, which is used to measure a temperature. It might be a barometer, which is used to measure a pressure, and piezoelectric, which is used to measure the vibrations, mechanical vibrations, and it convert it into the electrical signal. So they are actually acting like a transducers when I'll talk about the sensors. And after that, I have to convert them into the digital form. That's where the analog to digital converters are coming into the picture. There are a variety of analog to digital converters. It depends upon what kind of application you are dealing with. It might be a ramp type, it might be a dual slope integrator type. So it's entirely application specific. And then this processor part is coming into the picture. This, if I'll talk about the general purpose microcontroller, that means I'm talking about the PIC and ARM. So they are having the their internal architecture, and they are having the set of instructions which are having the ability to do the digital signal processing. This is the most important part when I use this word digital signal processing. So I'm going to discuss the digital signal processing part in embedded system. So these are the output interfaces, again, in order to relate with the outside world to convert your digital data into the analog form. So these are the examples. There are the plenty of examples of a embedded system in which the embedded system is used. In the printer, a small computer with the pre-planned instructions can be embedded into a printer. A cell phone, we are having the CMOS sensors and all. Automobile engine, brakes, dash. In the television, household appliances. The most important use of the embedded system in surveillance systems. But my focus is I'm trying to discuss the embedded system scenario corresponding to the one particular application, that is its use in wireless sensor network, because it's a emerging field and it's not possible to go through with all the applications of embedded system. So I'm trying to focus on a one particular application of embedded system, that is wireless sensor network. So where embedded system plays very important role in embedded system, that's what we are going to see in next of my slides. So let's before going into the embedded system part in wireless sensor network, let's go through with the basic introductory part to the wireless sensor network. What is wireless sensor network is all about. Okay, so that's why I have emphasized on the word that is micro electromechanical system. Okay, I have discussed this part, and of course highly integrated digital electronics, because whatever the data I'm getting from the outside world, which is actually in analog form, I have to convert it into the digital form until or unless I'm not able to apply any mathematical operations onto it. So that's why the digital electronics is also coming into the picture. And they have led to the development of microsensors. Of course, when I use this word microsensors, I'm talking about a very small sensors, a very micro size sensors I'm talking about. So everything is going to be small. This is the key thing, that if I have to design, if I'm go through with any application specific thing, then these sensors are deployed in that particular area where I have to sense something or I have to do some task. They deploy there, and together they are performing a task, a application specific task, in an organized manner. So they are forming a network, and that network is called as your wireless sensor network. And the most important thing, these sensors are obviously equipped with data processing and communication abilities. Data processing, that's where the embedded system part is coming into the picture. When I'm talking about the data processing, because the data that I'm getting from the outside world, it has to be processed. Okay. And communication abilities means I'm talking about that the data which we are getting, that transmitted to the neighboring nodes, neighboring wireless sensor nodes. Okay, that's where the communication capabilities are coming into the picture. So all these things needs to be happen at a very small data rate. The cost of doing this thing needs to be very small. That is the very important thing, because if the cost of the sensor node is going to be high, then the entire cost of the wireless sensor network is going to be high, and that's not our criteria. Our objective is that the cost is one of our objective, obviously, and I'm also going to discuss the other objectives which we have to taken care of when we going with the when we make some wireless sensor network. So each node consists of processing capabilities, one or more microcontrollers. That's where the embedded part is coming into the picture. CPUs or the DSP's chip. Radio frequencies transceivers means we are having the trans receivers which are doing both the things, which are transmitting the data and they are also receiving the data. And we are also having a power source, and this is the most important part, okay, the power source, because I'm talking about the sensors which are having a small size, so I'm not going to give a very large power to them. We cannot connect the large batteries to them, otherwise it is going to increase the cost. So power is one of the major constraints in a wireless sensor network which we have to take care of. And lot of power is going to be consumed when we do the processing task, the data processing task. Lot of power is consumed there uh, in order to process the signals. So this is our main important thing, that how we can reduce this power consumption. So this is the architecture point of view of a wireless sensor network. As you can see, sensing units, there are two sensing units which are connected here, and we are there we are having the sensors and analog to digital converters. Sensors is obviously is basically performing your sensing tasks. It's depends upon you in what area you are deploying the nodes, what kind of physical variations you want to sense. So according to that, that particular sensors are taken into the account. I've already given the examples like barometers for pressure measuring, thermometers for temperatures. So the sensors are performing, doing their sensing tasks. And once your signals are basically sensed by the sensors, they have to be converted into the digital form. And that's where the analog to digital converters are coming into the picture. That's what I've already told you. And the data, that digital form of the data, is transmitted to the processing unit. And that's where your embedded part is coming into the picture. That processing part might be your microcontroller. It can be your PIC, ARM, or that could be your DSP processors, FPGA, it's field programmable gate array, CPLDs. So this processing unit can be anything, but now right now we are talking about the embedded system. So we are main concentrate on the PIC or the ARM, which can be used here at the processing unit. And then the trans receiver part, through which that is connected to the antenna, through which we are transmitting or receiving, because that is going to do both the tasks simultaneously, and we are transmitting and receiving the data from the neighboring nodes. Okay. The power unit, this is very important, because power unit is going to give the power to your embedded system. It is going to give a power to your embedded system. So all the processing task which is going to happen in this processing unit, a lot of power is going to be consumed here. Okay. If you are, because there are a lot of data that is coming from the real world, uh, there might be possibility that redundant data is coming, so processor have to process that data again and again. So at that time the lot of power is going to consume. And when we are transmitting the data to the neighboring nodes, there the data is also there the power is also consumed, because you are transmitting it to the neighboring nodes. So that's why we have to taken care of this thing. Because why the power is so important, why I'm again and again emphasizing on this part, because we have a limited sources to give power to the sensor node. And the wireless sensor nodes are basically deployed in hard to reach locations. It means you cannot change the battery all the time. If a sensor node is going to die, you cannot change its battery. For example, if you deploy the sensor nodes in a volcano, you cannot go there and just change the sensor nodes. And suppose you are deploying the nodes in a forest, so there are some hard to reach locations where you cannot just go and change the battery. So that's why this power unit must be taken care of, and we have to perform the thing so there becomes a less power consumption. That's why the compressive sensing is coming into the picture, that how can I compress the data which I'm going to compress without actually disrupting the originality of my signal. Okay, we are going to discuss that thing. And that's why the power unit is one of the very important constraints in wireless sensor network. And location finding system, this is related to if I have to keep the track of my sensor nodes, then this location finding system is coming to the picture. Power generator, it is basically providing the main power supply to my power unit. And the part is actuator. This is basically related to the controlling part, that is related to the controlling part of sensor node, because we are not just doing the sensing through the wireless sensor networks. Sometimes we have to just control the sensor nodes. When I use this word controlling the sensor node, that means sometimes we have to rotate the sensor nodes, uh, change the length of the change the location of the length of the sensor nodes. So that's where this controlling part is coming to the picture. And not internally, even externally. I mean, if I have to uh, uh, flow some or throw some fluid in outside environment, so I can do that by using these concepts of actuators. So this is wireless sensor network architecture. And let's talk about the mainly the processing unit, where the digital signal processors are coming into the picture. So these are the design factors which I've already discussed with you. What are the important design factors we have to taken care of while we are designing a wireless sensor network? These are the main important design factors where the lot of power is going to consume. One is the sensing task, where you are gathering the data from the real-time world. So the power is also consumed there. Communication means when you are transmitting that data to the neighboring sensor nodes, there the power is going to be consumed. And of course the data processing part, uh, where you have to process the data, the digital data that you are getting from the sensor nodes. You have to process that. So in processing, in computation, the lot of power is going to consume. Okay. So what are the network services that has been provided, by which we can avoid this thing, by which we can save our power? The two of them are compression and aggregation, and both of them are basically reduce the communication cost and increase the reliability of data transfer. When I use this word data compression, that means we are considering one as a sync node, and all the sensor nodes are going or transmitting the data to that particularly one sync node. So we are actually aggregating that data to a one sync node, because that might be possibilities that the sensor networks, the sensor nodes which are gathering the data, that might be redundant in nature. You are gathering again same data again and again. So it's very important that we can find out the redundancy in data, because that is a very important thing. Why we have to waste our resources or a power on a redundant data, the same data. So it's very important that how we can distinguish the redundant data from our useful data. That's where the concepts of digital signal processings are coming into the picture. One of the example is you can use the autocorrelation function, which can gives you the similarities or the patterns among the data. Once you see the patterns among your data, then it's quite easy to compress it by using the mathematical operations, mean, variance, or you can use the Fourier transform, wavelet transform. There are plenty of transforms are there. So, but the important thing is that we do not have to disturb the originality of the data. I mean, if you are compressing the data, it's important that original data is not is not uh, is not going to be disturbed. Okay, so this is the very important thing while you're doing the data compression. Okay, so let's talk about the digital signal processors and what are the main features of digital signal processors, and what are the difficulties which we are having while processing the data, and how these difficulties can be avoided by using the concepts of compressive sensing. So digital signal processors, why signal processors are important? Obviously because they are situated, an embedded system is situated in an external environment, and your sensors are basically providing the data to you. They are going to sense the data, okay, and that data needs to be processed. That's where the digital signal processors are coming into the picture, and that's what I've already discussed. What sensors are going to sense, it entirely depends upon what kind of application you are dealing with. It's application dependent thing. Okay. uh, it depends upon your application. That might be you can measure weight, velocity, acceleration, electrical currents, voltage, or temperatures. Different sensors are used in order to measure these physical changes. Okay, this is the one of the example, that is your image sensor. uh, your lot of sensors you are having a lot of sensors in your cell phones also. uh, Let me give you one example, like a proximity sensors. I think you are aware with this term, proximity sensors. uh, it's the proximity sensors is quite used in by the Motorola in their cell phones. You can see this proximity sensors near your front camera, or you can also see them where you put your earplugs. The small dots are there. These are basically your proximity sensors. What they do basically, while you are listening somebody call, and when you take your phone near to your ear, they just shut down the screen in order to save the battery. And it's like when you wave your hand over the cell phone, its screen flashes, or its screen just on. That's where the proximity sensors are coming into the picture. How they do that? They basically sending some infrared light of millimeter range. So when any object basically when any object is coming into that range, in that range, they basically do the particular task which they have assigned for. So like image sensors are basically going to sense the images. The idea is basically they are having the plenty of cells. These cells are basically made up of capacitors, and we already aware with the concepts of capacitors that they are going to accumulate the charge, and those charges are going to be accumulate. That entirely depends upon the intensity of the light. So in order to convert it into the current form, that charges are basically integrated over a period of time. That time window is very small. and and we know that because I is equals to dq by dt. So basically you can integrate the charges over the time, so you're getting the current. And once you get the current, then basically you can convert it into the digital form. That's the analog. That current is analog in nature, and you can convert that current into the digital form by using the ADC concepts operating. And that ADCs are operating at pixel rate. When I use this word pixel rate, that means I'm talking about a very small time window in which I have to gather the data, in which I have to take the data from the pixels per frame. So we have to take care of this thing. What are the features of digital signal processors, or what are the, while we are performing the DSP tasks, what important things which we have to consider of. uh, what are the DSP tasks requires? Repetitive numeric computations. That's what I've already told you, that you are getting the redundant data, or the data that you are getting from the real-time world. You have to uh, perform the computations on it. Attention to the numeric fidelity, high memory bandwidth. Obviously when you have to process such a huge amount of data, the bandwidth requirement is going to increase. And this is one of the disadvantage, because this is not our objective. Because if I'm talking about the role of the embedded system in wireless sensor network, I need the bandwidth requirement to be small, otherwise it will going to increase my cost. And I already told you that if I'm talking about a huge wireless sensor network, the cost is one of the major issues. And real-time processing, of course, we are gathering the data from the real time. We can deploy these nodes in some hills in order to predict the landslides. Or we can also having these nodes in a we can place them in a forest or somewhere else where we can perform the flood detection tasks. So yes, real-time processing is there. DSP must perform this task efficiently while minimizing. So these are the very important parts, very important constraints from any designing point of view: cost, power, memory use, and obviously the development time. Okay. So let's discuss the compressive sensing. This is the one of the very important and uh, emerging field, compressive sensing, in the field of digital signal processing. That how we can compress the data without affecting the originality of my original signal. How can I compress my signal? Okay. So compressive sensing is a novel theory of compressive sensing, also come under the terminologies of compressed sensing, compressive sampling, or sparse recovery, which provides a fundamentally new approach for efficiently acquiring and reconstructing a signal from relatively few measurements. I mean, we're already familiar with the concepts of Shannon's sampling theorem, or the Nyquist criteria. We know that. And we have to fulfill this criteria if I have to reconstruct my original signal. That means we already aware with this mathematical expression, that is Fs equals to 2Fm. Uh, Fs equals to 2Fm. This is your sampling frequency. And this is your original signal, that is your modulating signal frequency. So if I have to reconstruct my original signal, suppose if I'm having any continuous signal, this is a band unlimited signal. Obviously, I'm talking about here band limited signal, but I have taken this example for just from understanding point of view. Suppose this is the signal, if I'm taking into the account, and when I convert this signal into the digital form, and that signal can be converted into the digital form, you can use the impulse train. One of the simple thing, you just convolve it with the impulse train. Okay, this is your impulse train, and by using the properties of your impulse function, you can convert this signal into the digital form, or in the form of the samples. Okay, it will be like this. I mean, your continuous time signal is converted into the discrete form, and now you are having the samples at a particular time. So once you do that, but in order to reconstruct my original signal, of course, if I'm dealing with the real time, real world, I need my data should be in analog form. So when I have to convert my digital data back into the analog form, I have to follow this criteria, that is Nyquist criteria, that is Fs, that your sampling frequency needs to be greater than equals to 2Fm, and this is called as your oversampling. This is what I have told you is a critical sampling. Because when you pass your original signal, when you pass your signal, digital signal through reconstruction filter, which is your low pass filter, then it will going to reject all the other samples. It will going to give you the original sample, and it will going to reject all the other samples. So why so much samples are taken into the account? This will going to waste our memory resources. This will going to increase our cost, and we also need a more bandwidth in order to store such a huge amount of samples. I mean, in order to reconstruct my original signal, I need almost double the samples which for my original signals, which I'm taking my which the signals or the samples which I'm taking into the account in the starting. Means in order to reconstruct my original signal, I need almost double the samples of my original signal. So there is a so in order to avoid this thing, so that we can able to generate my original signal even with the Fs equals to Fm, the concept of compressive sensing is coming into the picture. Of course, here I'm talking about the undersampling, that the some of the data is going to be lost, but that's where the concepts of random measurements or probabilities, statistics, these concepts are coming into the picture. On the basis of the probability functions, we are going to reconstruct our original signal. There we have to consider what are data in the past, is there pattern there. So that's where the L1 minimization reconstruction algorithms are coming into the picture, and you can find its tool in a MATLAB also. It's there. So this is the one thing. So we can take the advantage of this thing in a wireless sensor network, where we have to process the data. So rather than processing that huge amount of data, we simply compress it by using the compressive sensing. And the most important thing, we can reconstruct it. So the thing is, but this compressive sensing is not possible until or unless we are not having the sparseness, until or unless we are not having the domain of the signals same. So it is very important that we have to consider this domain of the signals. into the account, they have to be converted into the sparse domain, they have to be converted into the frequency domain. Then only you can apply the concepts of compressive sensing, and converting them into the frequency domain, the Fourier transform or the wavelet transforms are coming to the picture. So this is the one thing we have to taken care of while using the concepts of compressive sensing. And there are two kind of compressions can be done. It can be either lossy or lossless. Lossless compression is basically reduces the bits by identifying and eliminating the statistical redundancy. It just avoids the redundancy. So there is no information is going to be lost. And the lossy compression, what lossy compression do? These techniques, they basically identifying that this information is unnecessary, and how they are identifying this information is unnecessary. Again, all the concepts of information theory are coming into the picture, because we know that the probability, how the probability is related with the information, okay, they are inversely proportional. If my bits are occurring again and again, then the less important is given to them. So we are basically removing it, that part of the information is not important anymore. So the compressive sensing is actually the type of the lossy compression, where we are just remove the unnecessary information, but we are still able to generate our original signals on the basis of those random metrics, which is also you can see it in the MATLAB, one of the functions of the MATLAB, or by using the L1 minimization reconstruction algorithms. Okay. This is one of the small example to represent the concept of compressive sensing, what I'm trying to discuss here. See, this is the X, this is the data which you are gathering, and this is the compressed version of the data. So by using this compression or the random projections, we are trying to generate a signal that is Y. So here this random projection means here the probability functions are coming into the picture. X, which I'm talking about, is a compressed version of the data. It's already been compressed, and by using this random projections, we are trying to generate a signal which is similar to my X signals, and then that Y is finally passed through the recovery or the L1 minimization algorithm, where we are generated our original signal, that is X. That's what I've already discussed. So the compressive sensing concepts are not feasible and cannot be applied until or unless the concept of spectrum estimation is not understood. What is that spectrum estimation and why it's so important? We have to consider the sparsity or the sparse signal into the account in order to do the compressive sensing. So the sparsity is very important part. So there we have to change the domain of the signal. Means if I'm talking about the time domain of the signal, we have to convert it into the frequency domain. And when I convert my signal into the frequency domain, it's very important that we have to find out the spectrum, or we have to do the spectrum estimation of our signal. Means spectrum means I'm referring the frequency content of a signal on which all the mathematical operations are going to be applied. So spectrum provides an identity or a signature for a signal. In sense, no other signal has the same spectrum. Two signals are never going to have the same spectrum. Okay, so it provides the identity to the signal or a signature. And information from the signal can be obtained directly or indirectly from the spectral content of the signal. For this, we have to perform the spectrum estimation. So in order to get the information from the signal, the real-time signal I'm talking about, the signals that we are sensing, the physical changes which we are talking about. So in order to get the information for those signals, we have to convert it into the, we need their spectrum. From their spectrum, we are going to basically get their information, what information they are having. We have to get their frequency content. Okay, so how we can get the frequency contents of the signals? That's where this one of the very famous transform that is called Fourier transform is coming into the picture, which is used to convert the signal from time domain to the frequency domain. Okay, so this is the forward kernel, that is xt raised to power minus 2j pi ft dt. That's its forward kernel, is shown, which is used to convert my time domain signal into the frequency domain. Okay, the entire xt is going to multiply it with this factor, and it is integrated over limits, and we are going to get the frequency domain of the signal. There's another transform that is wavelet transform. It's mathematical, or I can say that its forward kernel is shown in the figure, where tau is basically representing the location of the window, because there is a problem with the Fourier transform. That's why the wavelet transform is coming to the picture. What is the problem the Fourier transform is having? Fourier transform are the transform which actually works globally on the signal. It not works locally. When I use the word globally, that means when I'm applying the Fourier transform on a signal, it applied on the entire signal at once. Okay, so it's good if I'm talking about my signals which are periodic in nature. But if I'm talking about the non-periodic signals, because real-time signals are going to be non-periodic in nature, which are going to be changed at every point of time, at every instant. So there, the Fourier transforms cannot be used. That's where the wavelet transforms are coming into the picture. And the important thing about the wavelet transform is their window function. I mean, I'm talking about that space and time means you can just move this window, and you can get the frequency content, and you can do the frequency analysis of every part of the signal. Okay, so this is the window function. So this window functions can be move, or it can be expand by just varying the factors tau and s, and the circle part here is actually representing the window function. Okay, so this is the one of the example where it shows the window is moving, it moving further. And the next example is basically showing we are expanding that window, okay, by just varying those tau and s factors, and we are analyzing the different parts of the signal by using this. Why it is important? Because we need the spectrum estimation of the signal, and once we have the spectrum, we can talk about the compressive sensing. And if we are having the compressive sensing, then that is very important to save our power and our bandwidth requirements, and also in order to reduce our cost. So it is all that is related to that DSP processors. Okay, so this is one of the small uh, topic, that is compressive data gathering. I mean, recently the concepts of the compressive sensing are using into a compressive data gathering. So this compressive data gathering that has been which is based on the compressive sensing, that has been proposed and as a viable approach for the sensor network data collections. I mean, we are having the different sinks now, and we are going to apply the concepts of compressive sensing theory on those sinks, and they are going to compress our data, and that compressed version of the data is now transmitted. So that's where this compressive data gathering is coming into the picture. So now we are forming a network where we are dealing with the compressed version of the data. So they are forming now, the wireless sensor networks are forming a compressive data gathering network. Outliers in wireless sensor networks, and they are also going to affect our embedded systems. When I use this word outliers, that means when the measurements that significantly deviates from the normal pattern of sense data are considered as outliers. Means what measurements I actually required, if they deviate from their originality, that's where the outliers, that's what they do, outliers in wireless sensor networks. The potential, what are the sources of outliers? The potential sources of outliers basically includes noise, errors, the attacks on the networks. So these are the possible or the potential sources of outliers in the wireless sensor network. They are going to affect the nodes. So so that's why we have to taken care of these things, that even if my data is affected with the noise, I mean, the real-time data I'm getting, it's not like it is free from the noise. Obviously it is having some noise in it. So in that case, how I can get the original data from that noise version of the data? That's where I have to predict the pattern, I have to predict the noise, I have to see whether the noise is occurring in my data or not. Again, the digital signal processing concepts are coming into the picture. And once you get that, and then you have to remove it, of course, by using mathematical operations. So we have to taken care of these outliers also in wireless sensor networks, whether my sensor network is going to affect with the noise or not. So the one of the very important scenario of wireless sensor networks, from wireless sensor network point of view, and from embedded system point of view, that is power aware architecture. Okay, so why this power aware architecture is very important? That's what I've already told you, that while embedded system is performing some task, while it is doing some processing or while it is doing some data processing, the power is going to be consumed. The power is going to be consumed from the battery, and I already told you that there are some hard to reach locations where you cannot reach and just change the battery. So that's why we need the power aware architecture. So from designing point of view, from wireless sensor network designing point of view, we have to see what are the parameters or the components which are responsible for this power consumption, and what parameters we can dealt with, so that we can have the power management properly, or we are having the power aware architecture. So power consumption, why the power consumption is having, due to what reasons it is occurring, and what are the problems we are having due to the power consumption. Basically, if there is a lot of power is going to be consumed, we just cannot connect the big cooling systems. I know this is the one of the solution, that if a lot of power is going to be consumed, we can avoid it by just connecting a large number of coolers, coolings. But this is going to increase the cost, and obviously if I'm talking about the wireless sensor network, we cannot just connect big batteries, or we cannot just connect the big cooling systems, because we are talking about the micro sensors, the sensor nodes of very small size. So it is very important that we have to taken care of this issue, the power consumption. And secondly, if my temperature is going to be increased, that's where I'm going to discuss the concepts of hotspot. Due to that, my temperature is increased, and there is also the noise issues. I've already discussed the noise issues. Basically, the outliers, which are possible sources, are basically noise. One of the possible source of outlier is noise. So due to these reasons, the power consumption is going to occur. And what are the problems? That is compaction density and the reliability, and that is thermal failover limits. Basically due to the hotspots, because if I'm talking about the silicon chip on which all of my components are placed or integrated, then it might be the possibilities, and the power on that entire silicon chip is not uniformly distributed. If the power on the entire silicon chip is uniformly distributed, then there is no need to discuss the concept of power aware architecture, because power is distributed uniformly. But the power that is distributed on the silicon chip, it's not uniform. So it might be the possibility that at a single point, at a one point, at a one region, the power is going to be very high, corresponding to the second point. So if the power is going to be very high at that particular point, that's where this hotspot thing is occurring, and there at that particular region, the lot of power is going to be consumed. So that might basically damage our circuit. So we see what's the solution of this problem. But before discussing its solution, it's important to discuss the concept of power density. That means how we are going to measure the power. We are talking about the power, that power consumption is happening. These are the problems which we are having due to the power consumption. But the important thing is that how we are going to measure that power on a one particular area of a silicon chip. It's the formula that we already aware with it. It's measured by watts per centimeter square. The power that we are going to measure corresponding to the one particular area, that's why it is giving in the form of watts per centimeter square. Okay, and this is the problem, that's what I'm discussing. Power is not distributed evenly on the chip. A failure can happen if a single point reach the maximum point. That's what I'm telling about the problem of hotspot. And of course, if I'm talking about the digital signal processing task, the complex algorithms are coming into the picture in order to do the digital signal processing. There, the lot of power is going to be consumed in order to run those algorithms. And of course, the timing pressures is also the one of the constraints. We have to do the things in a particular time. The code is going to be executed in a particular time. So there might be the possibilities. So due to that, the lot of power is going to be consumed due to these timing pressures. So these are the main reasons that why the lot of power is going to be consumed. And so let's discuss what is the solution for this power consumption, that how we can avoid this problem of hotspot. uh, why this hotspot is occur means, I mean, a silicon is not a good heat conductor, but if from a designing point of view, if the two if the intensively lot of data is sharing between the two nodes, or the two components, if a lot of data is going to be shared, then obviously from the designing point of view, those components is placed nearer to each other. So when those components are basically placed nearer to each other, then it's obviously lot of power is going to be consumed at that particular points. Okay, so due to which a large power consumption is happening there. Also there becomes a high temperature at that point, that will lead to the high leakage, and that high leakage led to the again high power, which is again led to the high temperature. So this is forming a loop, and this loop is continuous again and again, and that will going to damage our chip or a circuit. It might be the failure of our entire application. So from the designing point of view, we need a smart layout. When I use this word smart layout, that means we have to separate those hot units. These hot units I have to separate from each other. Okay, so that will increase my processor's power envelope. Okay, so I have to place this processing units, sorry, hot units separates from each other. This is the solution. So that will increase the my processor power envelope. When I use this word, what is the meaning of that processor power envelope? The power envelope, that is maximum power that can be dissipated via cooling technologies. Obviously you have to dissipate all the power so that the temperature is less, so that the leakage should be less, so that I can avoid the problem of this hot spots. And that maximum power so needs to be dissipated by the cooling technologies. So I have to increase this power envelope by putting this hot units separate from each other, and that's come under the designing part, and that's what is the meaning of smart layout. So power dissipation, what is the meaning of power dissipation here? See, a bigger system cool better and dissipate more power, obviously. And so the important thing that matters in order to avoid this problem of power consumption, we cannot have the bigger systems to cool. Obviously, we cannot have them. I'm already told you, because I'm talking about the micro sensors. This will going to increase my cost. So this cannot be the solution. One of the solutions I already told you, that from the designing point of view, I can place my hot sensing, my hot units separate from each other. And another thing is that average power density matters. That is the uniform distribution of the power over the entire chip. That is the solution. That is one of the solution, and that is one of the important thing, that there should be the uniform. The power should be evenly distributed over the entire chip. So if the power is uniformly distributed over the entire chip, that allows the CPU to dissipate more power, so that there will be no leakage and we are not having the high temperatures. So how we can measure this power consumption, how the power consumption can be measured? We already aware with power can be given as by energy per unit time, and the watts is represented in joules per second. So the power density, I've already told you, that can be measured by power per unit area. On a particular chip area where you want to measure the power, okay, that's where I have to define this power density. And this energy delay product is very important, and there is a trade-off between this energy and delay. And this energy and delay are together considered as a single term. They are not considered as a different term. The energy is given as energy per instructions. So that means if I'm going to increase my supply voltage, let's say VDD, if I'm going to increase my supply voltage, that will going to increase my energy consumption. On the other hand, it will going to decrease my delay. And if I'm going to reduce my supply voltage, that is VDD, so the energy consumption is going to reduce, but on the other hand, my delay is going to increase. So that means there is a trade-off between energy and delay. That's why their product is actually considered as a single term. And the most important thing is that, because if your delay is going to reduce, that means we have to see that the execution time of the codes, that is going to reduce. So it's a trade-off. If energy is reducing, on the other hand, the time to execute the codes is going to increases. So we have to taken care of this thing. What are the sources, main sources of power consumption? One of the sources, dynamic power consumption. Obviously, if I'm talking about the dynamic power consumption, the capacitors having the charging and discharging. Uh, so there, the lot of power is going to be consumed in capacitor charging and discharging, and the power is also be going to be consumed on the switching activity. When your CMOS transistors are going to be on and off, there the lot of power is going to consume. And obviously the short circuit currents, the short circuit path between the supply rails during the switching, there the lot of power is going to be consumed. And leakage currents, I mean, even if my transistor, the CMOS transistor is not on, the leaking diodes and transistors, due to them the power is going to consume. This is another trade-off between power versus speed, which we have to taken care of. See, in order to achieve high performance, we need to put all the components that frequently talk to each other as close as possible. So this is the important thing from the designing point of view. Those components which frequently talk to each other, which is intensively transmitting or receiving data from each other. Okay, we have to place them as close as possible, but placing close together is going to lead to the problem of our hotspot, which I've told you, because if two components are going to place uh, in a same place, in going to be placed very close to each other, then the problem of hotspot is going to be occur. Lot of power is going to consume there, that will going to increase our temperature. Again, that loop is going to be formed. On the other hand, if hotspot cause high leakage, that increase the temperature. That's what I've already told you. So that in order to avoid that problem, I mean hotspot, we have to place the components separate from each other, and we have to reduce the frequency. But reducing the frequency, that we have to reduce the speed. So it's very important that we need to, from the designing point of view, there is a trade-off between power and speed. So we have to take care of that thing. We have to manage both of these constraints. This is the one of the mathematical expressions which will tell you how the power is going to be consumed in of CMOS circuits, and it is given by P is equals to alpha CL VDD ka square F. So see, the power is depending. Alpha is the switching activity, CL is the load capacitance, but the important thing is here is VDD, that is the supply voltage. So my power that is going to be consumed, it is directly depends upon the supply voltage, and it will directly depends upon the frequency. So if we are going to reduce the supply voltage, then obviously the power consumption is going to be reduced, but it will also going to decrease our frequency, that will going to reduce our speed. So that's why that will basically, reducing frequency will going to increase our time, so that the runtime of the algorithms is going to be increased, the executing time of the algorithms is going to be increased. So that's what we don't want. So that's why I have discussed the trade-off between the power and speed. So decreasing the supply voltage, if I decrease the supply voltage somehow, I'm able to reduce the power consumption quadratically. As you see, it's a square relation, so I can reduce that power quadratically. But if I'm reduce that power, if I'm going to reduce the power by reducing the supply voltage, as you see, this is the delay formulation. CL is the load capacitance, VDD is the supply voltage, and VT is the threshold voltage. I mean, uh, VT is the minimum voltage that you required in order to make your CMOS on. So we need that minimum amount of voltage. So until or unless your VDD is not going to be greater than the VT, your CMOS is not going to be on. So I need my supply voltage needs to be greater than my threshold voltage in order to make my CMOS on. So that means the VDD minus VT ka square is going to be much greater than VDD. So it becomes VDD square. So ultimately my delay time is inversely proportional to VDD. So if I'm going to reduce my supply voltage, I'm reducing my supply voltage so that my power consumption is going to be reduced. So I have to, so the runtime of the algorithms is going to be increased. That's why I've discussed this relations. So it's a trade-off between the power consumption and the speed and the delay time. So if you're reducing the power, it will going to increase the delay, the runtime of the algorithms. So what are the power saving strategies which we have to follow? uh, One is reduce the power supply voltage, which we are discussing again and again. Run at the lower clock frequencies. Disable function units with control signals when not in use. Means it's like when you're talking about the above 2 points are basically from the circuit design point of view. The last 2 points is basically from the architecture point of view. So while you are designing, it's not like that all the parts of your architectures or all the part of your designs are working. By giving the proper control signals, you can disable them. One of the examples is like you are having the floating point unit, and if it is performing the integer operation, it's not like you have to use all the resistors in order to perform that integer operation. You can basically disable some of the shift resistors while performing that operation, while performing the uh, floating point unit operation. Disconnect the parts from the power supply when not in use. I mean, it's not disabling, it's basically not, it's putting into the sleep mode. Just remove those parts from the power supply when some parts are not in use. So these are the strategies which we follow in order to save the power. And most importantly, that these strategies are put into the other forms. What are the other forms? Like gating. It's clock gating. Here we are disabling the clock, deactivate the clock to unused resistors. I mean, by using we are just disabling the clock signals corresponding to those resistors which we are not using. This is one of the solution. Another solution is the signal gating. I mean, deactivate signal that cause activity if not used. This is basically for address buses or the data buses which are not in use. You can just disable it by using this signal gating. And the power gating is basically the most important part, that you have to deactivate VDD, I mean the main supply voltage. That is very important for unused hardware blocks. So by this, you can just remove the VDD, and we have already seen from that relation that the power consumption is going to be reduced if your VDD is going to be reduced. And these are power down modes. These are the another way of representing those signal gating, clock gating, and the power gating. So I've already told you these power down modes are basically controlled by the software or user. And the CPUs can provide multiple power modes, but I'm discussing three of modes with you. Uh, and the generic modes, there is basically ideal mode, that is clock distribution turned off. It is again come under the category of clock gating, which I've already discussed, that we can give the clock to the some of the shift resistors which we are not using. We can disable them in order to save the power. Nap mode, the cache memory is turned off on the chip. And the sleep mode, that is turn off the power to the unused processor logic. I mean, just completely put it into the sleep mode in order to save the power. That's where the power gating is coming into the picture, the third point, which I have discussed in the previous slide. So how we can so the dynamic power management, how actually the dynamic power can be managed. When a device becomes idle, it transition to a lower power usage stage. uh, when your device becomes idle, it can transition to the lower power usage stage, one of the solution. Second is a fixed amount of additional time and energy are required to transition back to the active state when new requests for services arise. So, but the thing is, when is going to be the best time to transition to the sleep state? When you are going to put your circuit into the sleep state, when it is going to be the best time? Too soon. If you're going to do that very quickly in the starting, in the initialization, then you have to pay startup cost too frequently. The startup cost is going to be increased. Okay. If you are going to do this thing too late, then there is a lot of time is going to be you have wasted too much time because a lot of power is consumed. So we have to do these things very properly. So generally, this is the solution. The transition to the sleep state, when the cost of being in active state is at least the cost of waking up. Means you do the transition to the sleep stage when the cost of being in active state is at least of the waking up. If this trade-off is not going to be satisfied, there is no use of no use of doing this power modes and all. the dynamic power management concept is failed there if this trade-off is not going to satisfy. One of the example is pick. To conserve power, pick can be put into the sleep mode. In order to conserve power in the pick, it can be put into the sleep mode, and its oscillator circuit is basically turned off, and devices basically stop executing this code. Okay, so if I'm going to conclude my lecture, so the overall thing is that my entire focus is on that, uh, how the digital signal processors are going to consume a lot of power in the processing, in their processing. The signals that you are getting from the real-time world, the a lot of power is going to be consumed in their processing. And secondly, how we can avoid this power consumption by using the concepts of compressive sensing, where we are just not following the Nyquist criteria, but still somehow we are able to regenerate our original signal by using the L1 minimization algorithms. And there are plenty of other algorithms. There are a lot of mathematics there. It's not just a small thing, compressive sensing, but I have just give you the idea that yes, it is possible that we can compress the data without following our Nyquist criteria. This is one of the important thing. And the most important thing, the another scenario of the embedded system, what I have discussed with you, is the power aware architecture, which is also very important from the wireless sensor point of view, because you are using the embedded system in wireless sensor network also, that when your nodes are not working, you can put it into the sleep mode, and but you have to follow that criteria or a trade-off which I have discussed, the trade-off between the power and the delays. So these are the some aspects of the embedded system, and how the embedded system can be placed into a wireless sensor network. Thank you. So, any questions? If you have any questions, you can ask. Yes, do you have any questions? So you can ask. तो वो दे दो ना तो वो दे दो ना कुछ PVP Siddharth. So PVP Siddharth College. If you have doubt regarding this lecture or in any topic.
Hello. Good afternoon, sir.
Good afternoon, sir.
Good afternoon.
What is the importance of location finding system in wireless sensor network architecture?
Sir, location finding systems means if I have to keep track of my wireless sensor nodes, that's where the concepts of GPS are coming into the picture. I mean, if you are performing any application and you are deploying your nodes somewhere, and you want to know the locations of them, because there are some hard to reach locations where you cannot reach, and you need to keep the track of your nodes, that whether they are doing their task properly or not. So you have to keep the track of them. So you have to be aware with their locations. So that's where this locating system part is coming to the picture.
Sir, one more doubt, sir.
Sure.
You have given power gating.
Yes.
Can you explain why importance of power gating?
Yes. Importance of power gating.
Yes.
Yes, okay. Power gating is basically very important, because if you have seen, I have shown you one of the mathematical expressions related to a CMOS, that how it is depends upon the supply voltage. That the relation is basically the quadratic relationship, that's VDD ka square. That's what I have shown you. So in the power gating, if you are able to reduce the supply voltage, and if you are somehow cut the supply voltage when you are not using your circuit, and when you are not doing any work, you are going to reduce the power consumption. So it's very important from the wireless sensor point of view, because the power consumption can be reduced, because when your nodes are not working, I mean, if you are not taking any work from your nodes, then there is no need to basically to make them on. So they can be basically shut down or put it into the sleep mode by using the power gating concept.